Well, okay. Recording a video or a series of videos for a class that I have stuck in the midst of the semester, or second, near the middle of the semester. We're moving towards the end. I wanted to move this up forward, so there was also videos for what I believe used to be class like 23. So this would actually fit into right around class 17 instead. Where we're going to look at shaft design early so that we can use statics for shaft design. So we're going to design the shaft based on stress and strength, and take a look at some miscellaneous components, and then design a shaft for static stress and strength. So here's an example of the type of shaft that we're going to design. Would fit into a gearbox that looks something like this, or a rendering of one at least. And we're going to do a step shaft. I'm going to highlight in the intermediate shaft, right? So we have an input, probably over on this side, right there, and have something like maybe a motor running into it. We go to this gear, and this gear is going to be high speed. This one's going to be slower because this is a smaller gear to a larger gear. And then this shaft right here is going to transmit that power over to this other smaller gear right there, which is also going to do another step down to make even slower, and then this would be the output where we would put a load. And so if you could look at the path that the power is going to be constant all the way through. Power in equals power out, but the torque is going to be small and the speed high right here. And so we're going to have a path that comes in through here, transmitted into there. Now the speed reduces, but the torque increases, and then transmitted through there, and then through here, and then through there. So you can kind of like see the load path that's being where the energy is being transmitted. And so we're going to have slow speed here and high torque, but the same power. Another rendering of a gearbox here, and this is just this is also two-stage right here. You just can't quite see. So we have come through here. There's a bearing right here. So this shaft and this shaft are not connected to each other. So there's actually two bearings right in there for this. The end of this shaft right here comes into there, and these are helical gears, notably. And so we're transmitting from little gear to big gear through this intermediate shaft. Here's a little gear to big gear, and then the output right there. We're going to have a project. We're going to start in the first part of it. We're going to design this shaft for, but based on static. Later on, we'll do fatigue design. And our most important deliverable here is going to be a well-dimensioned drawing. This is just an example one. I put together, I guess, in spring of 2019. I believe this one has the basic or geometry dimensions. I put them as XX just to, you have to kind of come up with these dimensions. Don't put the XX's in there, please. But I believe this is for the example that's in chapter 7 that they go through. And once again, that chapter 7 is designing it for fatigue. So it's not, the example is not exactly a roadmap for what we're going to do. And here's like another picture of this drawing. I want you to use this title block, and this is 11 by 17 orientation. We call that a B size. And make sure that when you make it in SolidWorks, don't give me the SolidWorks file. Turn it into a PDF. I can't open your SolidWorks drawing file. Do not give it to me. I don't want to open it. Here is in chapter 18 of Shigley. Chapter 18 is a transmission design sort of study where we're kind of putting it together. Some of the stuff from chapter 7, some of the stuff from the bearing chapter, some of the stuff from the gear chapters. I'll put it together into a sort of a project type of thing. So it's relevant to what we're doing. So you might want to check out chapter 18. We'll be doing some more stuff like that in ME470. But this is sort of like a precursor. But here they're showing their dimension drawing. They have several features on here we're not going to include. Some of these little snapper ring things or little flat grooves, we're not putting those into there. And their keyway is kind of weird. So here we start with the introduction to this topic, or the introduction to chapter 7. I should say I should get rid of the page numbers because they're probably not correct anymore. That's probably the 9th edition actually. So when we work through the design, our main considerations are going to be stress, deflection, and vibration. That's just typical for a shaft. Things you might want to consider. And here's the thing we're doing in this section right here. We're going to consider static strength, but we also would later want to consider what fatigue. We might also to check. We might need a design for it, but we would have some kind of criteria how much deflection we were going to be allowed in bending. So a lot of times that has to do with if you have gears involved. You don't want there to be too much deflection, because then the gear amount of gear, the gear interface, the amount of the meshing between them is going to change when the shafts move apart from each other. So you want to have a significantly stiff enough so that it doesn't have a negative impact on how the gears are interfacing with each other. It also might have some kind of deflection issues in terms of the surrounding equipment or even the housing or whatever. It might need to have designed it so that it was a fairly close fit, and so there's not going to be perhaps enough gap between the edge of the gear and the housing. If the shaft is too flexible, you could rub up against the housing. That type of idea in the deflection. We want to double check it's not too much. I can't think of different torsional deflection types of limits. I can't think of them. So I'm not quite sure when this would become applicable, but maybe I'm just not creative enough to come up with a criteria that you would want to say, hey, don't have too much torsional deflection. But here's a good one. I had the slope at the ends of at the bearings, right? Because we're treating these things like simply supported beams, but the bearings really aren't really a good simply supported model. They're close enough, but they have a sort of a limit to how much deflection slope right here that you can have, and how much the bearing will allow for that type of sloping, or I'm trying to find angular deflection, let's say. And then, of course, we're worried about natural frequency and sympathetic resonance. We don't want our shaft to have a natural frequency that is close to its operating speed. It gets all crazy when that happens. Our main equations for a shaft, because it's transmitting power, that we have power is torque times RPM. And so this is the one when we're using US units that we go through, because we could take our inch pounds and our RPM and we can get horsepower out of them. So using this equation when it's US units, when it's SI, we'd use this equation, notably that we're going watts, not kilowatts, so pay attention to that. There's actually another equation, so I'm not sure why I don't have it here. This is just using for radians per second, but we also have an equation. I should really open up the book and write it down. It's in that same section. I'm not sure why I don't have it here already, but we also have, and I don't know why they didn't write it the other way, but they wrote this: torque is equal to 9.55 H over N, and this H is in watts, so it's not kilowatts, and this N is in RPM. So this is sort of like the equivalent equation to be using compared to when you're using SI. Use this equation. When you're using US, use this equation for relationship between torque, power, and RPM. This design list here for shaft design is quite similar to other types of projects, right? in the sense that of this arrangement, which needs an E in there. It's interesting. Um, and the layout. This comes first. Arrangement is king. When you go to start a design, how the thing will look is the first part of it. Whether you're designing a shaft or the next widget. Um, for instance, a friend has asked me to help them design the housing for this soil testing technology they're trying to develop, and they're trying to figure out how to make it ergonomically useful, but also visually appealing. It's all about the shape of the thing, and you know, there's also how the stuff fits on into the inside. What do the guts look like? How does it attach to the thing that well, it's going to be attaching to a jar with different jars with different fluids. One of them being the soil sample, you know, mixed up with some water as part of the thing. So just trying to how when I go to design, when I'm working on the design, what is the layout? What is the arrangement? That's the first part of it. Um, and then the next, we got to figure out what the loads are. Okay, so we just had this right here. Here's the beginning of the load section. We could get the torque, and if we get the torque, we get the force, and where the force is located, and how much are they, and then we start to get where the once you get the loads, we need the supports, right? The reaction forces, and then you need the shear moment diagram. So that's all right here in the loads. We have to pick a material, and it doesn't have to be in this order. But there's a lot more to material selection, and we'll talk a little bit about that. But it's kind of there's more to it than just, hey, let's pick this steel just because we like it. We put a lot of thought into it, and you might need to come and revisit it because material will have a lot to do with how much something costs, which is inevitably part of what we do in a design. When you get all those things, you can start picking out what the diameters are, and that's where like the equations, most you know the strength and stress, their interaction, and the safety factor or design factor that you're putting in here. This is where that all comes into place, and then you start getting into the details, right? So this section right here, from here down, are the details. And I've often thought that you make you don't want to go too far down this path until you've settled in these guys, right? So there might be a sort of a loop that you, or a lot of times, most people actually draw it the other way. We have a design spiral until we work through the thing, and then we have to maybe come back and visit it, and then so we land into all of these things are worked out, and then maybe we want one to come down into here, right? So don't go too quickly into in a real world design. Selecting all of these things. Sometimes they might be chosen for you, but if you get down to this level right here, and then then you find out there's changes, you've done a lot of waste, right? So maybe here's really where the most deep, maybe these two right here, it'd be a lot of waste if you had to go back up into your design. These are just pictures I got off of another another textbook, and some of the idea is lying back up into the layout thing. So this is the reason why I'm showing these. You start to look at features and how, where parts go, and the different choices that are made on how to attach things, and where, other things you might want to consider. Like there's some kind of some type of a seal. Seals are like really important, and they can, there's something in your design you have to consider. You want to make sure that if this is a housing and they're showing, this thing just continues up right here. Let's say that the thing that we just haven't seen the limits of the thing. There might be some pressure inside here. Could be some fluid that wants to get out and leak and make a mess. So the seals are quite important, and in different pieces of equipment with rotating shaft. Um, there's sometimes we need to have the actuation of things. I have some type of clutch. and we might need to this one's showing it's got a spline, and this piece there's springs right here, so this piece right here can shift back and forth. So here's your clutch right in there. So here's and this is pretty much cantilevered, hanging off of from this support, because here's the bearings placed on here. This has a belt coming onto here. So the main point of this is, although we're making a our example is very similar to some of the other gear problems that we've done. There's a lot more to this. There's a lot of machines that have shafts, and there's a lot of different arrangement choices to be made. So, but we begin most of the time with some type of layout and arrangement. Let's say in our case, somebody has decided for us that the bearings are going to be located here. And nope, I'm sorry, I said it wrong. They're here and here, right? And so this is going to be a pinion that has overhanging the gear, and here's another gear. So we have here's the basic axial layout, and so these things actually have a certain amount of width to them, so we have to accommodate for that. And then we have to design the shaft, and there's got to be places we like to have locations where it has a step here to make sure that when installed, these gears are and bearings are exactly where that we want them to be on lengthwise, axially. So there was some discussion in the layout. Shaft materials. This can be quite complex. I think I alluded in class to the Ashby diagram. So let me, in the show here, discard that. And let's see, I'll just go to Ashby. Let's see if it'll let me type in here. Ashby diagram. Spelled wrong. Diagram. So here's our Ashby diagrams. I'll go to images and let's see if we can find one that'll open up. Here's one right here. Okay, so this is an interesting one. This goes with temperature. This one, I'm not sure what that'll open up into. All right, so here's a more typical here where we have density versus Young's modulus. And there's interesting, it has these lines there right here, right? And these guidelines, you can create kind of without using numbers, just using the basic formulas for a scenario, let's say a bending scenario, and rearranging them, you could isolate and come up with these figures, and they might be the elastic modulus over density, or the square root of the elastic modulus over density, cube root of elastic modulus over density. But anyway, that could be like something that we establish as well. In our situation, this combination of variables is pertinent, and then you could take a parallel lines to this and try to find equivalent or ranges of potential alternate materials that you might want to consider that have this same ratio of traits. So that's kind of like the idea for the lines. And this is done by Granta, which was a company formed by Mr. Ashby. I guess he might be a doctor, Dr. Ashby. And I believe they were purchased, Granta, which has software to do these things on various combinations, right? So this one right here was like sort of like density and stiffness. If those are the primary concerns in your design, here's an Ashby chart that you might want to use. Same thing true here's with strength and density, where you might want a low density, high strength might be our priority in what we're designing for a piece, and so you would use this Ashby chart. Same thing truth was now if you did strength and stiffness, so like density wasn't the big primary driver of your design. I think there's also even some cost ones in here. So you can see that this could be quite more complex, and you can put a lot more thought into it than just simply picking some material. So you can go systematically and try to find where the cost benefits or and narrow down to a particular material that's going to be the most optimum for your design. We don't do that, but it's good to know. It's good for you to know that it exists. Now, I think that this is getting a little long, this video. I guess I'll just keep going with it. So I apologize if it's a too long a video. You can just make my voice faster, skip ahead. I decided to put a little bit more stuff about cost into our project. So I found this here at Engineer's Edge, and this is for the estimating costs of um, the machining. Right, so first I'll actually maybe jump to here where I found some cost on online metals right here, online metals, and I for round bar, and they had it's this collection of carbon steel, and it had some alloy steel, some stainless steel, and some aluminum. So I would like you to consider looking and trying to have a cost estimate. So select from here. I looked up a 2-inch diameter by 36-inch long bar. Ours might be smaller than that. And here's the density. Most steel has a pretty much the same density, regardless of its amount of alloy material. Pretty much true. And then, so I figured out what the volume was of this 2-inch by 36 long round bar, and then then dollars. I got rid of the column. You don't see it. And then I went so it cost per volume, and then I went with used the pounds per volume, and I got dollars per pound. Right. So that's what we really care about. Find how much the thing weigh, and then multiply this by that, and you'll end up getting how much it costs. I got a elastic modulus because that's a stiffness concern. Yield strength, that's what we're going to use. We also need to know ultimate strength because when we go for fatigue stuff, it's all based on ultimate, basically. And then I also got machinability, and I got all of that off of MATLab. And so you'll see how we use that in the example. Most of these we won't use anything for stiffness yet, and we won't do anything with ultimate strength yet, but it's something we want to consider. So anyway, that's the acquisition cost, but we also want to say how much does it cost to make this, and some of them are kind of similar. It depends on what the diameters you pick. You want to find the volume of the stock, right? So we're going to keep it simple and make the largest diameter. We'll say that's the stock that we want to buy. When we choose diameters, we're going to choose them by preferred sizes, but we also we might want to go to online metals and see do they sell them in your largest diameter. You might have to even go up a little larger to be able to buy it. So that's and you'll be able to find out what the cost is to buy actually the stock by itself. But once you have that volume of that stock, you find out the volume of your finished thing, right? You get that in SolidWorks pretty easy, and then you subtract the two right there. Other things now we're going to be the material removal minutes per volume. That's really going to be decided by your machinist. We are going to, this is a shaft, so we're going to use a lathe, and it's going to remove. And they give us something like 2 minutes per cubic inch, and then 0.02, right? So that's a pretty wide range. Well, let's just pick in between. We don't know. So without knowing, we will go 2 minutes per cubic inch is going to be the best we can do. And now you have, say, okay, now we have the shop rate. How much? Well, let's not go too crazy. We'll pretend like we don't know, and so we will get rid of the machine shop overhead. We might want to do some setup We might come up with a jig or something, or whatever we're machining, but we're not going to build with that. And for the lot quantity, we're just going to have one, right? We're just going to build one for the time being. So what we really need is, lastly, is this rate, right? So we established a rule of thumb from experience somehow, and we kind of just picked that up because it was in the middle. But now we need this rate, and that rate is going to be how dollars per hour. Well, if you look up a machine, you say what is the going wage for a machinist? And experienced machinists probably somewhere around $50 an hour, which comes out to about $100,000 a year. Let's say that it's, and then you say the low one. In the middle, what I saw online, and I'm not sure it's up to date, was about $25 an hour. But that's for the person's take-home pay. It also costs the company a bunch of overhead to have an employee. There's health insurance and other things and benefits. So let's just multiply it by 2, right? And I have seen that that's actually been a thing when estimating stuff to use 2. I've also heard 2.5, depending on industry and benefits and all that. There's also, where we withhold payroll tax from the employee, but they're also the employer pays some of the payroll tax. So it's more than just the wages, right? So we're going to go with $50 an hour in our company for this employee's time. So we've now going to be able to have a rough estimate of how much the shaft is going to cost in terms of, and this is a preliminary one. We have material acquisition cost, and we also have manufacturing costs. There can be some other costs involved, but this is just the beginning of us trying to come up with a number. See, shaft layout, I'd already talked about the axial layout, and of course the bearing locations, but also some of the details where the bearings land up against this step of the shaft, right? So the purpose of the step is to definitively establish when you put a piece of equipment, when you put the gear or the bearing onto the shaft, that it is exactly there in the axial layout and will match. Some considerations is that transition that happens between one step and another step, right? So I guess that's actually right there. And so we often will want, and these are weird by all 3 of these I've never seen, or do I recall seeing on a shaft? But most of the time we'll have going from one diameter to another. We will make a little fillet right in there. You have to make sure that that fillet is not as big or it's not bigger than the fillet that's on the bearing. It has a little bit of a fillet. We need to have a smaller fillet. Zooming into the thing, I should have put a little fillet in there. So here is our little fillet right there. The thing that's laying up against it, it needs to have a bigger one, so as not to run into it. Like if you had too big of a fillet right here on our part, now here is the part right there I was trying to draw, like that makes sense right there. So the one I just drew, this is the bearing part right here. Its fillet is smaller than the shaft. Here's the shaft right there, and this will be interfere with each other. Okay, so that's the idea. Other things to consider is the assembly and disassembly, and that's not going to be in our project, but make sure that you think ahead of for maintenance and people just disassembling something, and also when they build it. There's a lot of consideration to be placed there. I'm going in the wrong direction here, but the different types of loads and where they're at. We've kind of made an assumption that we know what the axial layout is. It might be the case in the real world where we find that we're stuck and we can't build a sensible shaft. And a lot of that has to do with somebody made the thing too long, right? Having a long shaft means you're going to have large bending loads. maybe it's better to go back and revisit the axial location of stuff. And that's all about like the main thing that you're doing is you're transmitting power, and where those things are located. That might be something that you want to try to look for, um, revisiting. I'm sorry. Some of those things that we have might have axial loads. For instance, if you had like a fan and you were supporting it right here, this fan might be blowing air, but if it's blowing air, it's having a reaction coming this way. So your bearings need to be able to support, at least one of them needs to be support an axial load. If you have a helical gear running on something, as opposed to a spur gear, right? Spur gear will could draw like this right here. Looks like spurs. This just has, when looked at, it has a tangential and a radial load, right? The radial load is a necessary thing because the gear teeth, they have a arc to them, and so a gear teeth looks like this. I don't need to teach you all of this, but the force, of mating teeth are going to be perpendicular to the two surfaces right there where they're aligned with each other, and therefore you have a tangential component that's the purpose of the gear, but you also have a radial component as a consequence of that. For helical gears, not only do you have those two, but you also have an axial force, because reaction force, because they're placed in that way. So you have to account for that. So the supportive axial loads are things to consider. Obviously, we're transmitting power, so therefore we have to transmit torque. There's going to be a torque interaction going on right there. Last, I'll come back to the diameters. This diameter and this diameter, there's only a range that makes sense. And the book gives us some amount of guidance here of what the D over D is going to be, right? So here's the big D, and this looks a lot like and is related to the stress concentration tables here. But so consider when when calculating the diameters and then picking the preferred sizes. Also note that when you make a transition so that you have an axial location for a gear or a bearing, that we also need to keep within this range. So sort of a balancing act of those considerations. We do need to know widths, so the gear ones need to be told, but we can also find standard widths from table 11.2. So we jump to chapter 11. They have like a sample gear, a sample bearing catalog page, and there are bearings that come in different proportions. Their designations are quite often with a 0 and then a number. But 002 bearings are probably the most common, I suppose. And so those sort of have a family of sizes. So maybe I ought to go to that right now. Let's see how we're doing in time. 33 minutes. I need to shorten this up here. But let me go to books and go to Shigley and just show you what I'm talking about in that section. So I should have made this a shorter video. Yeah. Oh well. So here in chapter 11 is our rolling bearings, and they give you better dimensions of what bearings look like. But the bore diameter and the width and how tall they are as well, we don't care about that, are established by like like a family of numbers. Let's see if we could get to them. Okay, so here is the table, and so here's the bore. That's the inside diameter. So that's the matching one that would match up with our shaft. They need to be the same diameters right here. But we also have the width of them. They're established by these being O2 series bearings. And right here, okay, so here is the figure I wanted to show that we the O2. So I'm trying to get their width. Boom. Where'd you go? Fit to width. All right, so you can see here's the O2 family right here, O2 family, and that you have other ones that you could possibly have. So here's the width series. Okay, I guess you have also 1 and 2 and 3, but these O2 ones are the most common. All right, so we'll go back to our table here. And so that's other things that we will consider. And there's some pictures out of the book of different arrangements. There's part of the housing. We don't care about that right now, but how we establish. Oh, here's one. We notice there's a seal right there, or something that's representing a seal. There are many different types of seals. Here's also some housing considerations. The details do matter, but we're not going to have to worry about them. I'm not covering that in ME470 with any more additional detail than we're discussing that they exist. This is an interesting little feature right there. There's a ton of variations that exist, and if you were to be doing this in the real world, you would become an expert in your field. Is how to accomplish the same tasks right here. All right, so this is where we will make a stop and pick up from there. All right, so let me go out here, discard, and make a new video if it'll let me. Where'd you go, buddy? There you go. Talk to you soon.